On the map, the Gulf of Mexico looks harmless, just a curved basin tucked against the southern edge of the United States. But that seemingly ordinary stretch of water hides forces powerful enough to shape hurricanes, economies, and even the climate of an entire continent. This single body of water helps power the strongest hurricanes in the Atlantic, drains nearly half of the United States, and sits above one of the largest oil reserves on Earth. And yet, its influence reaches far beyond North America. Every second, enormous rivers of warm water escape the Gulf, forming the Gulf Stream, a current so powerful that it helps keep an entire continent, Europe, from freezing. In other words, the climate of cities like London, Paris, and Dublin is partly controlled by a body of water sitting next to Texas. So, how did a place that looks like a simple coastal gulf become one of the most powerful climate engines on the planet? Why does America's tiny ocean seem to defy geography? On the map, the Gulf of Mexico looks like little more than a curved indentation along America's southern coastline. But once you begin to measure it, the illusion quickly disappears. Covering roughly 1.6 million square kilometers, about 615,000 square miles, the Gulf is enormous. It's larger than many countries and wide enough to swallow the entire state of Texas twice over with room to spare. In terms of sheer scale, it behaves far less like a coastal gulf and far more like a small ocean basin of its own. And it isn't just wide, it's deep. Across most of the basin, the seafloor lies around 1,600 meters below the surface, while the deepest point, a remote abyss known as Sigsbee Deep, plunges more than 4,300 meters into darkness. Beneath those waters lies an immense geological archive. In some places, layers of sediment piled up by ancient rivers reach over 10 kilometers thick, burying the Gulf's ancient history deep beneath the seafloor. Yet, the true secret of the Gulf isn't simply its size or depth. It's the way the basin is shaped. Unlike the open Atlantic, the Gulf of Mexico is almost completely enclosed by land. North America curves around its northern edge, Mexico seals off the south and west, and Cuba helps close the basin to the southeast. In fact, the Gulf connects to the wider Atlantic through only two narrow gateways, the Yucatan Channel and the Straits of Florida. That geography turns the entire basin into something unusual, a vast natural reservoir where water, heat, and energy slowly accumulate. Oceanographers often describe it as a gigantic bathtub for the Atlantic, collecting warm water and circulating it within the basin before releasing it through just a few narrow exits. And that simple geographic design, an immense basin with only two narrow doors, is the quiet mechanism behind everything that makes the Gulf of Mexico so powerful. The Gulf of Mexico doesn't just receive water from the ocean, it receives water from an entire continent. Nearly 40% of the land area of the United States ultimately drains into this single basin. More than 30 major river systems carry rain, snowmelt, and sediment across thousands of miles before emptying into the Gulf. And towering above all of them is the Mississippi River. Stretching more than 3,700 kilometers, the Mississippi is the largest drainage system in North America, a vast network of rivers that collects water from the Rockies, the Great Plains, and the American Midwest before funneling it south toward the Gulf. But the Mississippi doesn't just carry water. Every year, it delivers roughly 500 million tons of sediment, soil eroded from farms, forests, and mountains across the heart of the continent. Over thousands of years, that sediment built one of the most remarkable landscapes in North America, the Mississippi River Delta in Louisiana. Grain by grain, the river pushed the coastline outward, creating wetlands, marshes, and new land where there had once been open water. For millennia, the Mississippi was literally building Louisiana. But today, that story has taken a dramatic turn. Louisiana is now losing land at one of the fastest rates anywhere on Earth. On average, an area of coastal land roughly the size of a football field disappears every 90 minutes. In other words, the same river system that once built the coastline is now part of the process that's causing it to vanish. To understand why the Gulf of Mexico is so unusual, we have to go back about 200 million years, to a time when the continents looked nothing like they do today. Back then, most of Earth's land was fused together into a single supercontinent known as Pangaea. As this massive landmass began to slowly tear apart, North and South America started drifting away from one another. In the gap that opened between them, a shallow basin began to form, the early foundation of what would eventually become the Gulf of Mexico. But this basin behaved in a very strange way. At times, it connected to the open ocean, allowing seawater to flood in. Then, as tectonic shifts altered the landscape, that connection would close again, trapping vast quantities of seawater inside the basin. Under the intense heat of the ancient Mesozoic climate, that trapped water began to evaporate. And when seawater evaporates, it leaves one thing behind: salt. This cycle, flooding, isolation, and evaporation, repeated itself over millions of years, gradually building an astonishing geological feature beneath the Gulf, a massive layer of salt that, in some places, grew 8 to 10 kilometers thick. But the story didn't end there. Salt behaves differently from most types of rock. Under immense pressure, it can slowly flow, almost like extremely thick honey. And because salt is slightly less dense than the rocks surrounding it, those buried salt layers eventually began pushing upward through the sediment above them. Over millions of years, they formed towering underground structures known as salt domes. And those strange geological structures would go on to shape the destiny of the entire region. As the salt domes pushed upward, they bent and warped the surrounding rock layers, creating perfect traps where oil and natural gas could accumulate. Today, those ancient geological processes have turned the Gulf of Mexico into one of the most important energy basins on Earth. Roughly 15% of all crude oil produced in the United States now comes from fields scattered across the Gulf. In other words, beneath the warm waters of the Gulf lies not just an ocean basin, but the geological engine of America's energy economy. Because of its position near the tropics and its nearly enclosed shape, the Gulf of Mexico absorbs and stores heat with remarkable efficiency. Throughout the long summer months, sunlight pours into the basin, warming its waters day after day. By late summer, sea surface temperatures across much of the Gulf routinely climb to around 29 to 31 degrees Celsius, among the warmest waters in the entire Atlantic basin. But the true secret of the Gulf's power lies beneath the surface. Flowing north from the Caribbean is a powerful current known as the Loop Current, a massive river of warm ocean water that pushes deep into the Gulf before bending eastward and exiting through the Straits of Florida. Unlike the thin, warm layers found in many parts of the ocean, the Loop Current carries heat far below the surface. In some places, its warm waters extend 800 to nearly 1,000 meters deep, storing an enormous amount of thermal energy throughout the water column. And sometimes, that current does something even more unusual. Large rings of warm water, known as loop current eddies, can break away and drift across the Gulf like slow-moving pools of stored heat. Some of these eddies are hundreds of kilometers wide and extend nearly a kilometer deep, acting like giant reservoirs of energy beneath the surface. The result is something extraordinary. A vast basin where heat doesn't just sit at the surface, but accumulates deep below the waves. In effect, the Gulf of Mexico behaves like a gigantic thermal battery for the Atlantic Ocean, slowly charging with heat throughout the summer. And when a tropical storm passes over that deep reservoir of warm water, that stored energy can be released with explosive force. Storms that cross the Gulf often intensify with astonishing speed, sometimes strengthening an entire category in less than a day. It's one of the key reasons why some of the most powerful hurricanes in modern history, from Katrina to Michael and Ian, have all rapidly intensified over the warm waters of the Gulf of Mexico. Because beneath its calm surface, the Gulf isn't just warm water, it's stored energy waiting to be unleashed. And when that immense reservoir of heat meets the right atmospheric conditions, the results can be explosive. At their core, hurricanes are giant heat engines. They draw energy from warm ocean water, converting that heat into powerful winds, towering storm clouds, and torrential rain. The warmer the water beneath them, the more fuel these storms can extract. And few places on Earth provide better fuel than the Gulf of Mexico. When a developing tropical storm drifts into the Gulf, it often encounters water temperatures exceeding 29 degrees Celsius, with warmth extending hundreds of meters below the surface. That deep layer of stored heat allows the storm to keep feeding on energy without quickly cooling the ocean beneath it. The result can be a dramatic process known as rapid intensification, when a storm's wind speeds increase by at least 35 miles per hour in less than 24 hours. Over the past 2 decades, some of the most destructive hurricanes in modern history have undergone this explosive strengthening over the Gulf's warm waters. Hurricane Katrina in 2005 intensified into a catastrophic Category 5 storm over the central Gulf. Hurricane Harvey in 2017 drew enormous moisture from the Gulf, unleashing record-breaking rainfall across Texas. And Hurricane Ian in 2022 rapidly strengthened before striking Florida as one of the most powerful storms in U.S. history. Because of this unique combination of warm water, deep heat reserves, and atmospheric conditions, the Gulf of Mexico has become one of the most dangerous hurricane incubators on the planet. What looks like a calm blue basin on the map is, in reality, a powerful natural engine, one capable of transforming ordinary tropical storms into devastating hurricanes. But the Mississippi River doesn't just carry sediment into the Gulf of Mexico. It carries something far less visible and far more troubling. Every year, rain washes enormous amounts of fertilizer runoff from farms across the American Midwest into the Mississippi River system. Those nutrients, primarily nitrogen and phosphorus, are essential for growing crops across the heartland of the United States. But once they reach the Gulf, they trigger a chain reaction. Scientists estimate that the Mississippi River delivers roughly 1.5 million tons of nitrogen into the Gulf of Mexico every single year. That sudden surge of nutrients fuels massive blooms of algae, spreading across the warm surface waters. At first, the explosion of algae seems like an abundance of life. But when the algae die, they sink and begin to decompose. Bacteria feeding on this organic matter consume enormous amounts of oxygen in the surrounding water. As oxygen levels drop, marine life begins to suffocate. Fish, shrimp, and crabs are forced to flee. Creatures that cannot escape simply die. The result is a vast region of ocean with dangerously low oxygen levels, what scientists call a hypoxic zone, more commonly known as a dead zone. In the Gulf of Mexico, this dead zone forms almost every summer. In particularly severe years, it can spread across more than 22,000 square kilometers, an area roughly the size of the U.S. state of New Jersey. It is now the largest dead zone in North America, and one of the largest anywhere on Earth, and that creates a remarkable paradox. The same river system that helps feed the agricultural heartland of the United States is also responsible for creating one of the largest dead zones on the planet just offshore in the Gulf of Mexico. But the Gulf of Mexico doesn't keep all of that heat to itself. Some of it escapes. As warm water leaves the Gulf through the Straits of Florida, it forms one of the most powerful ocean currents on Earth, the Gulf Stream. This immense current acts like a massive river flowing within the Atlantic Ocean. Every second, it transports roughly 150 million cubic meters of water northward along the eastern coast of the United States, more than 3,000 times the flow of the Mississippi River. But the Gulf Stream isn't just moving water, it's moving heat. As this warm current travels across the Atlantic, it carries enormous amounts of tropical warmth toward higher latitudes. When that heat is released into the atmosphere, it dramatically alters the climate of Western Europe. This is the final and perhaps most astonishing twist of the Gulf's story. Cities such as London, Dublin, and Paris sit at roughly the same latitude as places like Newfoundland and southern Canada. Yet their winters are far milder. While Canadian cities at that latitude are often locked in snow and ice, Western Europe remains comparatively warm and habitable. And a major reason for that difference is the heat carried out of the Gulf of Mexico by the Gulf Stream. In other words, the climate of an entire continent, thousands of kilometers away, is partly shaped by the warm waters that accumulate in a basin just off the coast of the United States. What appears on the map as a simple gulf is, in reality, one of the most important engines of Earth's climate system. But the story of the Gulf of Mexico isn't finished. In fact, it may be entering a new chapter. Over the past few decades, scientists have observed that the waters of the Gulf are warming faster than the global ocean average. Marine heat waves are becoming more frequent, and in some summers, surface temperatures have climbed well above 30 degrees Celsius. That extra heat matters. Because hurricanes are essentially heat engines, warmer waters give storms even more fuel. Researchers have already documented a rise in rapid intensification events, where tropical storms strengthen dramatically in a matter of hours. For communities along the Gulf Coast, from Texas to Florida, this could mean future hurricane seasons becoming more powerful, more unpredictable, and more dangerous. And that brings us back to the central mystery of the Gulf of Mexico. On the map, it appears deceptively simple, a wide curve of water along the southern edge of North America. But in reality, the Gulf is far more than a gulf. It is the place where an entire continent drains into the sea. It sits atop one of the richest energy basins on Earth. It stores vast amounts of heat capable of powering the most destructive hurricanes in the Atlantic. And it sends that heat across the ocean through the Gulf Stream, helping shape the climate of Western Europe thousands of kilometers away. Geology, rivers, ocean currents, and climate all converge in this single basin. So, the Gulf of Mexico is not just a body of water along America's coastline. It is, in many ways, a small ocean hiding in plain sight. A powerful engine quietly influencing weather, ecosystems, and human history across an entire planet. And that is why America's tiny ocean truly defies geography. If you enjoyed exploring the hidden forces shaping our planet, consider subscribing to the channel for more stories about the geography, science, and history behind the world around us.